Imagine hiking a rough, hilly road with many dips. The lowest one is hard to find. You could stroll into a small dip, swear it's the bottom, when a far deeper valley waits over the next rise. Now picture a single, smooth, U-shaped valley. Here there's no confusion. Any dip you find in the middle simply is the lowest point. Nowhere else for the bottom to hide. That single ball behavior has a name: convexity. It's the property that makes optimization trustworthy. And quietly, the reason so much of machine learning works. Here is the whole idea in one picture. Everything else flows from it. Take a bowl-shaped curve and pick any 2 points on it. Now stretch a straight line between them, a chord. Look where it sits. It rides above the curve the whole way across, while the curve sags below. And this isn't a lucky choice. Slide them anywhere, wide apart, close together, both on one side. Every time, the chord stays on top. That is exactly what it means for a function to be convex. Flip the ball into a dome, and the story reverses. Now the chord lies below the curve. A function whose chords all fall below it is called concave, the mirror image of convex. And a wiggly curve like this is neither. Draw a chord, and in some stretches, the curve dips below it. In others, it pokes above. A function can be convex, concave, or, very often, neither. Let's turn that picture into exact mathematics. Take 2 points x and y. Any point between them is a blend lambda times x plus 1 minus lambda times y, as lambda slides from 0 to 1. Convex means this one inequality holds for every pair and every lambda. On the left, the height of the curve at that in-between point. On the right, the height of the chord there. Convex says curve, at most chord. Read the two sides of the picture. This term is the curve, this term the chord. That little less than or equal sign is the entire definition of convexity. Make it concrete with x squared. Take x minus 1, y 2, lambda 1 half. The midpoint is 0.5, and the curve there, 0.25, comes out well below the chord's 2.5. The inequality holds just as the picture promised. When it's strictly less, we say strictly convex. Checking chords for every pair is a lot of work. Happily, convex functions come with two shortcuts. The first uses tangent lines. Rest a tangent line against the curve at any point. For a convex function, that tangent lies entirely below the graph, touching at one point, while the curve arcs up and away on both sides. Now slide that tangent along the curve. It never once cuts through. At every position, it stays underneath. So a convex function always sits above all its tangent lines. The tangent underestimates it everywhere. In symbols, that reads like this. The curve is never below its tangent approximation from any base point A. A clean first-order test for convexity. The second shortcut is even easier, and the one you'll reach for most. It uses the second derivative, how the slope itself is changing. The rule is wonderfully direct. If f double prime is greater than or equal to 0 at every point, the function is convex. If it's strictly positive everywhere, strictly convex. And if f double prime is less than or equal to 0 everywhere, the function is concave. Here's the intuition. A positive second derivative means the slope keeps rising. Negative, then flat, then positive. And a slope that only rises traces out exactly that upward ball. Let's run the curvature test on a handful of everyday functions, so the labels stick. Watch the sign of f double prime decide each one, e to the x. Its second derivative is e to the x again, always positive. So it is convex, curving up everywhere. The natural log for positive x. Its second derivative is minus 1 over x squared, always negative. So ln is concave, a dome. X cubed. Its second derivative is 6x, which is negative for x below 0 and positive above. The sign flips, so x cubed is neither convex nor concave, and the absolute value of x. It has a sharp corner at 0, so there's no second derivative there. Yet, its chords still all lie above it. So by the chord definition, it's convex. A reminder that the curvature test is only a shortcut. The chord picture is the real definition. In more than one variable, the same idea lifts into higher dimensions. The single number f double prime is replaced by a matrix of second derivatives, the Hessian. And convex now means that Hessian is positive semi-definite everywhere. When the Hessian is positive semi-definite, the surface is a genuine bowl, curving upward in every direction at once. The multivariate twin of f double prime being non-negative, but make the surface rise one way and fall another, and you get a saddle. Its Hessian has mixed signs, so a saddle is not convex. One direction of downhill is all it takes to break the guarantee. Now the punchline. The single reason convexity matters so much. It's worth memorizing word for word. For a convex function, there is only one basin. Drop a ball anywhere and let it roll downhill. It can only end up at the true bottom. No false valleys to fall into. No way to get stuck. But on a non-convex landscape, disaster. The same ball settles into the nearest little dip, a local minimum that isn't the lowest point at all. The real global minimum sits over there, unreached. So once you know a problem is convex, life gets easy. Find one point where the slope is 0, and it's guaranteed to be the best answer there is. That's exactly why we design so many machine learning loss functions to be convex. There's a companion idea worth a quick word: a convex set. Same spirit. The segment between any 2 points must stay inside. Here's a rounded blob, a disk. Pick any 2 points in it and draw the line joining them. Try it, and every chord stays home, never leaving the set. Dent the shape inward, like this crescent, and it breaks. 2 points across the notch, and the segment between them slips outside. That single escaping chord makes it non-convex. And the two ideas link beautifully. A function is convex exactly when the region above its graph, its epigraph, is a convex set. The chord picture, in one tidy sentence. Let's put it all to work. Show that this function, x to the fourth plus 2x squared plus 1 is strictly convex, and find where it bottoms out. Differentiate. F prime is 4x cubed plus 4x, which factors as 4x times x squared plus 1. Differentiate again. F double prime is 12x squared plus 4, and 12x squared is never negative. So this stays at least 4 strictly positive for every real x. So f is strictly convex on the whole line. Set f prime to 0. 4x times x squared plus 1 equals 0. The second factor is never 0 for real x. So the only critical point is x equals 0. Evaluate there, f of 0 is just 1. And because the function is strictly convex, that flat spot isn't merely a local minimum. It's the one and only global minimum. The lowest value is 1 at x equals 0. One more on a closed interval. Minimize x squared minus 4x plus 5, but only between 0 and 3. Here's its graph, a piece of a parabola. F prime is 2x minus 4, and f double prime is 2 positive everywhere. So the function is strictly convex. Setting f prime to 0 gives the critical point x equals 2 inside our interval. But on a closed interval, the winner could also sit at an endpoint. So we check all three, x equals 2, and the ends, 0 and 3. Evaluate f at each. At the endpoint 0, f is 5. At the critical point 2, f is 4 minus 8 plus 5, 1. At the endpoint 3, f is 9 minus 12 plus 5, 2. The smallest is 1 at x equals 2, the global minimum, and strict convexity makes it unique. The biggest value here is 5, at the endpoint 0. Your turn, two quick ones. Is x to the fourth convex? And is the square root of x concave for positive x? Pause, reach for the second derivative, and decide before I do. For x to the fourth, the second derivative is 12x squared, never negative for any x. So f is convex. It's actually strictly convex everywhere, except right at 0, where its curvature momentarily flattens. For the square root, write it as x to the 1 half. Its second derivative is minus 1 quarter x to the minus 3 halves, negative for every positive x. So the square root is concave. If you named both correctly, you've genuinely got this. Trap 1. Checking the second derivative at a single point. That only shows the curve bends up there. Convexity needs f double prime non-negative across the whole interval. Trap 2. Assuming convex guarantees a minimum. F of x equals x is convex, yet slides to minus infinity. No minimum at all. You need a closed bounded domain, or the function rising at the edges. Trap 3. Flipping the sign convention. Convex opens upward. F double prime non-negative, the shape that holds water. Concave opens downward. Mixing those two up is the commonest slip. And trap 4. Ignoring the domain. On the interval 0 to 3, a critical point at minus 2 is simply irrelevant. Only candidates inside the interval, plus its endpoints, are in the running. Let's lock it all in. Convexity is the chord above the curve. The height at any blend never exceeds the chord's height there. The fastest check. F double prime non-negative across the whole domain means convex. Equivalently, the graph never dips below any of its tangent lines. The first order test. And the reason it all matters. For a convex function, every local minimum is automatically the global minimum. Find one flat spot and you've found the best there is. Master these 4 lines, and convexity will feel obvious.